Hello everyone, welcome to this class on gas dynamics. We will first start with the discussion on what gas dynamics is and how is it different from fluid dynamics. What will be the basic difference if it is fluid dynamics versus gas dynamics? What will you tell will be the difference? In simple fluid dynamics, which we talk about, density remains constant roughly. And when it goes to gas dynamics, we will talk about density changing. In a sense, we are talking about compressible gases. Okay? We are talking about compressible flow of gases. That is a better way to put it. We are interested in flow of gases, and now we are thinking compressible flow. So, first thing we need to understand is what is compressibility. That is the first thing we need to think about, compressibility. So, when we think about compressibility, how will we define compressibility? Something to do with density gradient should be related to density. How is it density changing? How will density change, and what are the various ways by which density of a gas element can change? You are comfortable with gas element, right? Like fluid element, we can say now it is gas element. We will say specifically gases. Okay. So, how can a fluid density change or a gas density? How can it change? Various processes. What all can it be? Change in pressure. Anything else? Change in temperature. I could heat or cool a gas, that will change its density, or I could think about changing its pressure, that is I can compress a gas or expand a gas. That is all the things I can do to the gas. So, now we will go write something on the board. We will say I will use this notation for specific volume, mass specific volume, that is volume per unit mass, and I put this cut for V to tell that it is volume, versus if there is no cut I will use it for velocity. Okay, we will keep it that way. We will write this as a function of temperature and pressure, because we know that these two can change it. Now we want to use simple calculus and tell differential change in this specific volume. I make it d. We will just write it dV by V. What will this be equal to? Do you guys know it already? So, I will just keep this 1 by V separate, and then we will just write dV in terms of derivatives with respect to each of the terms. Next time I will be more careful about the corner line. Okay. I will have these two terms. Of course, you have to tell that this derivative keeping pressure constant and this derivative is keeping temperature constant. Okay. So, this is your expansion, that is I heat the gas at constant pressure and that is expanding, and this is your isothermal compressibility. These are the two terms we are looking at. So, if there is any fractional change in volume, specific volume here, then it could be because of a small change in pressure or because of a small change in temperature. Okay. Now, we are more interested in thinking about this term if we are talking compressible fluid flow. Okay. It may also be changing because of heating or cooling. We are more interested in this term mainly. Okay. So, we are looking for a term which is something like this. This is the coefficient for that dP. Okay. If this is very high, then the fractional change in specific volume will be very high for a given change in pressure. When that happens, we call this highly compressible gas. Okay. That is the way we are going to look at it. So, this is related to compressibility. This is what we will call as compressibility of the gas. It can be written in terms of density also. What is specific volume? It is volume per unit mass. Density will be mass per unit volume, just reciprocal of it. I can write it in terms of density. Compressibility can be defined as this. Okay. This is also probably called compressibility, whichever way you look at it. Okay. In most of gas dynamics, we will think about this. This is easier to work with. So, we will typically think about density of a gas compared to specific volume of a gas. It is equivalent, just one is a reciprocal of the other. We will stick to this. Now, this is one way of looking at the compressibility, but if you go look at books, there are so many books for compressibility. They will tell you different definitions for compressible flows. One of the definitions happens to be, it is related to compressibility, where we will tell if the compressibility is very high, then we will call it a compressible flow. Other definitions exist. What are the others? I did not get that. What does that repeat?
We can define this compressibility in terms of bulk modulus of elasticity.
Yes, in a way the bulk modulus is related to this term. Okay. This is related to bulk modulus. Yes, we can express this in terms of bulk modulus. That is one way of doing it. There are other forms, as in terms of velocities. There is one way of defining how will I call a flow compressible flow. Mach number related. Okay. We will keep that also in mind. We will come back to it after some time, and I will just tell you roughly what it means. I am going to define something called a Mach number, which is a ratio of the fluid element velocity divided by the speed of sound at that local point in the flow. Okay. So, that will be the local Mach number of that fluid element. Okay. Why are we, and we are going to say that it is, if it is very low compared to 1, then we will call it incompressible, and if it is pretty high compared to 1 or even higher than 1, we will call it compressible flow. That is what we are looking at. Okay. Should there be a negative sign? I guess the term will come out to be, if you want to call it as a compressibility, if you want to call it as compressibility and you want to say I want to keep my compressibility positive, then I have to put a negative sign, or else what will happen is this density to pressure relation will be opposite to each other, right. No, not density to pressure, volume to pressure will be opposite to each other. I will have to put a minus sign if I want to think about it as bulk modulus. Okay. If I want to leave it like this, it should not affect. In here it will not be a negative sign. We will use only the density based term.
No need of put a negative sign there.
If we are looking at the density term,
density.
If we are looking at the density based term, if you are looking at specific volume term, then
pressure will be increased.
If pressure increases, typically volume decreases at constant temperature. So, dV by dP will be negative, but we want to call bulk modulus as a positive modulus quantity, right. So, if that is the case, then we will put a negative sign in front of it. Okay. But if we are using in density, it should not affect. Okay. If it is density, it should not affect at all. We will keep it the same. Okay. Now, we said something called Mach number, and we said if it is far less than 1, it is incompressible, otherwise it is a compressible fluid. Why are we comparing with A, which is speed of sound of that particular fluid element at that point. Why are we comparing with speed of sound? It's not just any reference. I could have picked speed of light if you want as a reference, but that's not what we picked. Sound travels by compression and rarefaction. Okay, how is that related to what I want to tell? Compressibility.
It's not affected by any obstacle and
We won't worry about obstacles right now in the flow. Even if it is flow with no obstacles, just clean flow, if it is Mach 3 flow, why are we comparing it with speed of sound? One answer is something like sound wave is related to compression and expansion of the gas fluid element locally. If I am speaking to you, I am sending compression expansion waves to you, right. That compression and expansion, how fast can I compress and expand the gas, will tell you how fast the fluid will go towards. A quick way of talking about compressibility, I always like giving this example, is imagine a metal rod and imagine air column exactly the same volume out there. Now what we are thinking is, I am going to take a hammer and hit the metal rod here, and I put my finger on the other end to see when I will first feel the wave, that there is something happening on this corner, when will I feel it on the other side. If I do the same thing on air, which one will I feel quicker? Same length, metal will be quicker. Why? Density is higher is not the answer. Molecules are far more closer, but that is not the answer, but that is related to that term compressibility sitting there. Quick answer is speed of sound. Any information that needs to travel from one point to another point goes through collision of molecules. Think about it, I hit with the hammer on this corner layer of the metal rod, those set of molecules or atoms sitting there, ion atoms, let us say it is iron rod, ion atoms sitting there are going to be displaced by this hammer. When they move, they collide with the next layer, and then that will collide with the next layer, next layer, next layer, and then how are they moving in? How does the last layer know that the first layer had something? By collision, this is the only process. And after the first few layers, the molecules do not know that it was because of the hammer that the molecules are moving. Only the first two layers may be knowing that it is because of the hammer. Other layers will just know that the first layer moved. That is the only thing it knows. If that is the only thing it knows, is just that there is a wave that is coming from that end into the metal medium, right. Just a wave that is going through this lattice of your medium, that metal rod. You know, lattice is just arrangement of metal inside the metal rod, or metal atoms inside the metal rod. So that is being displaced, and the lattice vibrations are going to send that wave in a particular speed only. It will not send it at any speed it feels like. For the particular material, for that particular temperature, there is just one particular speed at which it will go. That happens to be speed of sound in that medium. If I think about air, same concept. I have a, let us say, a tube which has air inside, and I hit with a hammer here. What will happen? That molecules are more random, they are going to move and push the next set of molecules, they are going to crash into the next layer of molecules. Now those molecules should move away to give way for this. Now these will go and crash into the next layer of molecules. Like that, that crashing process one into the other is slowly transferred from one end to the other, right. If I assume the molecules are sitting idle and in a particular matrix formation like in a lattice, then life is simple, I can tell first layer goes and collides with second layer, but that is not the case with gases. It is a little more flexible, they find gap between them. So when one molecule comes, it need not hit this one, it may just move off, in which case that wave did not really matter to the second layer, there is more gap, okay. so it will not effectively go that fast, it will go a little slower. So speed of sound in gas medium will be less than speed of sound in lattice based medium like solids. You know speed of sound of speed of sound in air at room temperature, rough number 340 meter per second, 340 for our kind of room temperatures, not in AC rooms and stuff. And if you think about metal rod, say steel, of the order of 5000 to 6000 meter per second. Okay. Now we know that if I hit, the wave travels faster in iron steel compared to air. That is what we just found out, right? It is moving in speed of sound. Where did sound come in here? We were talking about a wave of molecules moving with that information that hammer hit it. Suddenly I am talking sound. How did I link it with sound? What exactly happened there was one layer being displaced. Let us say this is one layer, this is the next layer, this is the layer that was hit by the hammer, this comes in, and now there is a short while when two layers are close by. What does that mean? Density of molecules here is higher, that means the gas is compressed locally. Gas, or it does not matter, even if it is steel rod, matrix is getting compressed locally, it is getting compressed. And what happens when this molecule layer moves to the next layer? This region gets expanded. So there is compression expansion waves going through from one end to the other when I hit with the hammer. That is what is happening, right? I am sending in compression expansion waves, which is what we call as sound waves, right? A loose definition for sound waves. Of course, you go talk to acoustics people, they will tell different definition for a sound wave. We will keep it as this: any wave which is a bunch of waves produced due to collision of molecules, that is what we will call as a compression expansion wave related to speed of sound. Actually it is related to sound, and the speed of which is what we will call as speed of sound. Now we are linking things with this Mach number expression. What do we want to say? We want to compare the velocity of the fluid with the speed of sound in that medium. So we are telling there is a fluid element. Now we do not have any steel or anything else, there is just air, and we are looking at air column. There is one fluid element which wants to move fast. Now as it is moving, it is trying to push the layer in front of it. There will be a sound wave going. Okay. If that sound wave reaches ahead and then tells that this fluid element here that this is moving, then my speed here is less than the speed of sound, right? Then my Mach number is less than 1. If I had the opposite case, that is fluid is going faster, much ahead of the collision waves traveling, then what will happen? By the time the wave goes and hits it, that fluid element, the fluid element here will also go and hit it. If that is the case, this fluid element does not know that this flow was happening. Okay. So what will happen to all the fluid elements in between? They get crushed. Okay. We will see that that is the flow behind the shock later, we will not get that far right now, that gets crushed. Okay. We will look at that, we will give you more physical feel as time goes. Okay. But that is the idea. Now we will get back to this name Mach. There was an eminent scientist Ernst Mach, who did pioneering work in explaining movement of sound waves in gases, explaining shock waves, blast waves. He did most of his work in blast waves. Okay, most of his major contributions are in blast waves, how blast wave propagates in time, if there is an explosion of a bomb, how far will I feel the pressure wave, that kind of work he did a lot. Okay. But he explained the Mach wave, Mach reflection, Mach wave, all that. It all became his contribution. There is a lot of it, so we just give, it is a very apt name, I would say, I support that. So, we will follow that Mach number. Okay. Now, we will go back to the original definition we got from you people, which is if Mach number is far less than 1, we will call it incompressible, and if it is higher than that low limit, whatever, if it is anywhere comparable to 1, higher than 1, far higher than 1, all that is compressible flow. Okay. We will keep it that way. This is another definition for it. Okay. We are given two definitions. We will try and link these two definitions at a later stage, not right now. We will find that they are all the same. Okay. Eventually, we will see that. Now, we will get a little more into the course. Okay. This course is predominantly designed as starting from basics, as if you are starting at undergraduate level. This is the first compressible course you are ever having after your high school. That is how we are starting with, but I want to build up to a point where you can do graduate analysis with it. Full level research level analysis you should be able to do with this. I am just trying to give you a lot of physical intuition in understanding these concepts than mathematical alone. Of course, I am going to give you a lot of mathematics, I will write a lot of differential equations on the board and all that, and give you a lot of mathematical derivations, but finally I want you to have this physical feel for things. If something is happening, you should start visualizing the wave traveling from one end to the other, and because of that, this is what should happen. You should be able to tell that. That is the way I am thinking I will design this course. If you are not getting any physical feel for it any time in the middle, just stop me and ask, then I will give you even better physical feel for it. Okay. Of course, any scientific analysis should start with laws of physics, and it uses a lot of math, then only we can understand anything. Engineering always starts with laws of thermodynamics and then laws of mechanics, which is again subset of laws of physics. Of course, we will ignore currently laws of gravity, electromagnetism, nuclear physics, whatever, we will ignore all those other laws. We will stick to only laws of thermodynamics, laws of mechanics. We will start deriving all kinds of governing differential equations which are essential for understanding this particular flow field system, as in compressible flows, any type of compressible flows. Once we have the differential equation, remaining thing is all about putting special boundary conditions, and you will solve different flow properties. Whichever flows you want, you can solve for it. That is the basic idea. So, now I have to start with basic thermodynamics. This is just a review, so hopefully you will understand this, and we will go through this quickly. Okay. But I will spend some time on laws of thermodynamics. But before that, we have to define what a system is. What is a system?
Collection of matter of identifiable parts.
Any part of the universe is a better definition. Any part of the universe which we are currently interested in. Okay. We are interested in looking at some property of, say, this small volume of gas, then this becomes my system. Then what is the surrounding? Everything else around this in the whole universe. Everything around this in the whole universe is now considered surroundings to this. Whatever we are interested in is called system. I may be interested in 2-3 systems together, maybe system A, system B, system C, and then everything around is surroundings. That is also a possibility. What is a closed system?
Only energy transfer takes place across the boundary.
There is no closed system, is just a system where there is no mass interaction with the surroundings. We won't call it just there is only energy interaction as of now, we will leave it, we can come back to it if you want. Okay. We will say closed system is a system where there is no mass interaction, mass exchange across the boundaries of the system. An open system is where mass exchange is allowed. Okay. An isolated system is no exchange of any interaction possible, nothing is interacting, completely isolated system. Okay. So in that specific case we do not need to look at the surroundings. If there is no interaction with the surroundings, thermodynamics is simpler, we will consider only this unit, nothing else. Okay. Next thing we need to define is a state. What is a state? State of a system. We are trying to define the system. We are going to tell it is applying so much force on the walls of my box, it is having so much temperature, it is having so much energy inside, it is having so many molecules inside. All that is a description of the system completely. If I can define the system completely, then all the defining statements I made put together forms your state. For our simple systems we are talking about, if I want to call a state, say I pick an example, I can tell this volume of gas here is at a particular pressure, particular temperature, and it is having a volume. That will tell me, that will enable me to tell you any property of this volume of the gas. If you want me to give any specific property, I will be able to give it. So I have defined it completely. Then I have defined the state. What all did I use? Pressure, temperature, and volume. Okay. Like that. How many such properties should I have to define a state completely? 2, at least 2. Okay. This needs a little more, so I will wait a little bit and come back to this. What is a process? It is a combination of states, not exactly a correct word to use. Some change, okay. From one state it is going to another state, okay. That change is what we call as a process. Now what is a path? It is a sequence of states that the system goes through in a process. From beginning to ending of the process, it went from this state to this state to this state to this state, and then the whole connection of all the states together becomes your path of the system, okay. Path for the particular process which the system undergoes. Now I needed the next definition before I go back and answer the previous statement, which is how many variables do I need to define a state. For that I need to define intensive and extensive properties. What is an intensive property? Those properties that depend on mass, that are independent of mass, okay, or size, or number of molecules in the mass, whatever. If it depends on all these quantities, then that is an extensive property, okay. Extensive mass, volume, or size, whichever way you look at it. Intensive will be it does not depend on those. Intensive properties, it does not depend on all that. Okay. How will I tell whether a property is intensive or extensive? Say I am giving you some crazy property which is Gibbs free energy per number of molecules. Does it depend on mass or not, or is it an intensive or extensive property? How will I tell? Okay, say I am going to tell you an example which is enthalpy per unit volume, it does not contain mass, so what is it? Okay, that is not an easy way of doing things, so I will give you a clean definition. or a simple experiment which you can do to find out whether it is extensive or intensive. Let us say we will do I have a box, this is one system, let us say system 1, and it has that particular property which we want to explore, whether it is extensive or intensive we want to explore. So, I have some property here, I will create exactly identical system one more, okay. Exactly identical system one more I created, I put them next to each other, remove the boundary between them. Now, I will call the new system as these two put together. If my property value doubled, then it is extensive. If it remained the same, then it will be intensive. Okay. A quick check, now we can do the analysis. Let us say I pick volume, volume doubled, right. If I have same volume one more, 1 meter cube and 1 meter cube became 2 meter cube, it doubled. So, volume is an extensive property. Okay. If I think about pressure, same pressure here and here, when I remove the wall in between it is still the same pressure inside. So, that will be intensive property. If I think about that specific case we picked, enthalpy per unit volume, let us say enthalpy per unit volume here is 1 joule per meter cube, same 1 joule per meter cube here. Now, I want to find enthalpy per volume for the whole unit, for whole full box. This will be 2 joules per 2 meter cube, which will be again 1 joule per meter cube. It did not change. Okay. So, that is an intensive property. Okay. You guys comfortable with this kind of easy check analysis? If you do this, you will never make a mistake. Now, we will go back and again ask the same question. To define a state of a system, how many properties do I need? One from extensive and one from intensive I hear. 2 intensive is enough if we are interested in intensive properties only. Okay. If we are interested in intensive properties only for our whole analysis, I need only 2 intensive properties. If I want some extensive quantity, then I need to give one of them at least as extensive. I could have it as 2 intensive, one extensive, or I could give you a special case which will work for some simple situations, 1 intensive, 1 extensive. Okay. That is also fine. Okay. So, that is what we typically need to define a system. Now, we will enter into laws of thermodynamics. We will go for zeroth law of thermodynamics. What is zeroth law of thermodynamics? Typically, you would have heard first law and second law. What is zeroth law of thermodynamics? Thermal equilibrium. Okay. If mechanical engineering heat transfer people taught you thermodynamics, yes, it is defined as equilibrium, thermal equilibrium. But we are beyond them. We are going to say not just heat transfer happens in my fluid, it can also have pressure variations, it can also have chemical reactions if I want. We will look at that one by one. It depends on how you define things. Thermal equilibrium does not contain everything. Thermodynamic equilibrium defines everything. We will get back to that. Okay. So, first we have to give the statement of zeroth law of thermodynamics, which will be, if I have a system A, I have a system B, and I have a system C. If I look at system A and system B and I say that they are in equilibrium, I have not defined the word equilibrium yet. If I say that these two are in equilibrium and I also say that these two are in equilibrium, A and C are in equilibrium, then zeroth law of thermodynamics states that these two are in equilibrium. This is a law which is needed for comparing systems. We are comparing one system with another system and saying what can be different between them. So in this analysis we came to a point where we need a definition for equilibrium. How will I tell that system A and system B are in equilibrium? Now we have to talk about different properties and tell system A and system B are in equilibrium if something is equal to that. If I tell that temperature A is equal to temperature of B, then we call this thermal equilibrium. What did I introduce here? A new variable called temperature. Okay. This is how temperature is introduced. We have introduced a concept called equilibrium, we have introduced a variable called temperature, okay, to tell that these two systems have the same degree of hotness, okay, that is your temperature. If temperature A and temperature B are same and temperature A and temperature C are same, then temperature of B and C are same. That is what is the actual statement we are looking for. Okay. What about mechanical equilibrium? Now we have to think about how can I have system A and system B in mechanical equilibrium between each other. Forces should be the same, and we are going to make an assumption about our gas here. We are going to make an assumption saying it is a simple compressible substance. A simple compressible substance is a substance where the only form of work that can be done mechanically on it happens to be compression work and nothing else. Okay. Only compression work, which means it is just that P delta V kind of work. That is the only form of work possible. Of course, you can still have heat transfer through it. That is another way of interaction with energy, that is thermal interaction, this is mechanical interaction. Okay. If I define that, then I ask for mechanical equilibrium. Now I can tell these two will be in equilibrium if the pressure of A and pressure of B are equal, then they will not apply force on each other. Okay. You guys see that? It does not matter what the volume is. I may have a case where A is a small system, B is a big system. I put them together, they do not interact mechanically here as long as the pressures are equal. They will not push against each other, or they are pushing equally, nothing happens. Okay. Pressure into area is your force, forces on both sides are equal, that is your mechanical equilibrium, right. So now we have introduced the concept of pressure. We introduced equilibrium concept. While we are defining equilibrium, we defined thermal equilibrium where we said temperature is needed, we had to define temperature. Then we said we had to define pressure for mechanical equilibrium. Now I will tell you one more thing, chemical equilibrium, where we will say we need to know the composition of the gases. If the composition here and composition here are exactly the same, then they will not start doing any crazy exchanges across it. Okay. Or when we go to chemical equilibrium of a given system, instead of comparing systems, if I just look at one system, they think about it even otherwise. They will say I look at the system now, 10 seconds from now, 10 hours from now, 10 days from now, whatever. If the composition of the gases inside do not change, then the system is in equilibrium. Even if it changes after 10,000 years, the system is no more in equilibrium. Okay, it may be changing very slowly, but if it changes, it is not considered to be in equilibrium. Okay. That is the idea of equilibrium in theory. The same thing here, temperature of A, temperature of B are equal, and I put them together, they will not exchange energy. Okay. They will just keep the same temperature in both of them. Okay. If that is the case, then they are in equilibrium. If they exchange energy, then they are not in equilibrium. Okay. If I have a hot metal and a cold metal, I put them together, hot metal will give energy to the cold metal. So they are not in equilibrium at that moment. If I wait long enough, they both will become same temperature, then it has reached equilibrium. Okay. After that, if I wait for 10,000 years, it may not change. That is the basic idea. Okay. So, we have defined if the temperatures of the two metal blocks have become the same, then it has reached thermal equilibrium. If the metal blocks are still having different temperatures and the hot metal is giving energy to the cold metal, then there is exchange of energy, which means it is not in equilibrium yet. If I wait long enough, it may exchange enough that they will become equal. At that point I can tell that the system is in equilibrium, not till that point. Okay. And from that point on, if I wait how much ever time, no change in temperature. But now I will take a practical example. I take a metal block 50 degrees Celsius, I take another metal block in this room, another 50 degrees Celsius, I put it here. What will happen? The room temperature is 25 degrees Celsius. Both the temperatures will lose equally, they will lose the energy equally. What is happening here? Exchanging with surroundings. Okay. When we talked about systems here, we did not consider anything else here, we just considered system A, system B. We did not have anything called as surroundings, which means we considered isolated systems. We did not have a surrounding. If we have a surrounding, of course I could take that into account by putting a big circle around this and call that region as D. Okay. If there is exchange between A and D, then A and D are not in equilibrium with each other. Okay. Maybe TA and TB are still equal, these two are in equilibrium with each other, but they are not in equilibrium with the surroundings. That was the example I just gave you. Okay. 50 degrees Celsius two metal blocks, they will not exchange heat within themselves, but they will give heat to all the air around. Okay. You should just be very clear about all this. Okay. That is zeroth law of thermodynamics, where we introduce the concept of equilibrium, introduce a variable called temperature for thermal equilibrium, introduced a variable called pressure for mechanical equilibrium, introduced a variable called composition, which is actually a whole bunch of variables, right, mole fraction of each of the species present inside. Say if it is air, nitrogen, oxygen, carbon dioxide, water vapor, everything, mole fraction of everything I had to give if I want to define the state very correctly. Okay. Now if I go for first law of thermodynamics, what does that say? Energy remains constant. Energy can never be created, energy cannot be destroyed. Such statements exist. Okay. Of course, we are neglecting nuclear reactions and stuff in this particular case. If you are taking into account nuclear reaction, then we will have energy to mass conversion should be taken into account. We will ignore that for now, does not affect us. Okay. The primary statement will be simply put, energy is conserved. Okay. What did I do with this law of thermodynamics? I introduced a variable called energy. We did not define anything very well. Okay. We just said there is something called energy. How do we define it? We have not defined it. We just told energy is a fundamental quantity which defines the state. We just said that. We will give expressions for it later. Okay. And then we are going to say systems can have exchange between one and another. System A and system B can exchange energy. Okay. But the overall energy of my complete system does not change. Overall energy of my universe never changes. That is the law we are going to keep. It does not change at all. Okay. Of course, in a simple compressible substance, the only kind of energy exchange with my system happens to be through heat exchange or through compression or expansion work, nothing else. We will not consider the case like I put a fan inside my system and rotate it, that is stirring of my gas, which we are ignoring as a simple compressible substance. Okay. We will not have stirring case. If I stir a gas for a long time, its temperature will increase. but we will neglect that kind of energy transfer. Okay. Now we go for second law of thermodynamics. What does that say? Direction of energy transfer. Okay, and I heard something called entropy there. Okay, so they are linked. The actual statement is something like there exists a quantity called entropy. We defined the word entropy suddenly, we introduced the word entropy in second law of thermodynamics. Okay, and then we say if there is a process that is naturally occurring in nature, then entropy must be increasing. Entropy of what must be increasing? Entropy of the universe must be increasing. A quick example is refrigerator. Think about a refrigerator. If I cool the system, entropy decreases. You would have already had a little bit of thermodynamics, I am just using it like this loosely statement. Okay. If I make the temperature go very, very low, molecules cannot move around, there is no energy for it, so they will just sit idle in one place. That is the most restricted condition, entropy will be the lowest. Okay. So if I take my gas to say 1 Kelvin or 0.01 Kelvin, then I will be in a situation where my entropy will be very, very low. But there are physicists doing such experiments. What are they doing really? They are using a very big refrigerator and they are having this small gas controlled to that 0.01 Kelvin, while all the other gases around in the whole room may be heated up. If you go feel your refrigerator backside, it will be very hot. It is taking the heat from inside and sending it outside, right. Net energy is still conserved, okay. But this process is naturally occurring. Why? I am cooling a small volume and heating a big volume. Okay. That is the idea. I am cooling a small volume and heating a big volume. Okay. That is what I am thinking about. So overall what happens is I have given heat to a large number of molecules, removed it from a small number of molecules, they are unhappy, but the large number of molecules which I gave heat to, they are all happy. Okay. So it is, in my opinion, it's the entropy is like how happy are the molecules in the universe. They want to be more and more disordered. If you give it lot more energy, they will move in random directions at whatever speeds, so they are more happy in a way, right. We will come back to this happy and entropy relation later, come back to it again. Okay. But when we think about isolated systems only, of course isolated system does not have a surrounding, right, it is only system. There only we will say ds is greater than 0 if you want a system to occur spontaneously, a process to occur spontaneously. Okay. That is the idea. Okay. If for a imaginary process which I think about, if ds is less than 0, that process will never occur in nature. Okay. Is this a law put by man on nature or is it something else? It is just law of nature, we do not know who put it, maybe it is the god, but nature obeys this. It is called law of nature for that reason, it is just law of nature. All the thermodynamic laws we defined are obeyed by nature. Okay. Laws of mechanics are also obeyed by nature, but part of them are used to define variables. Momentum has to be defined by first law, like that you have to define various laws. Okay. Even here zeroth law was used to define equilibrium, first law was used to think about energy, second law was used to think about entropy. Okay. Entropy. So we said that if I have these variables, I am sufficiently equipped. Who introduced
this entropy concept in thermodynamics?
It was introduced somewhere around 1800s by I do not remember the exact set of people, but Gibbs was one of them, and then Boltzmann came and defined or gave numbers to it and gave a universal scale by which we can measure entropy and all that. Okay. So, that is where we are right now. We will go to next class and we will talk more about other thermodynamic variables. Okay. Other thermodynamic variables, we still have not gone to gas yet, perfect gas. We will have to define a gas, then we will define perfect gas, then we will go further along that direction, and then we will enter thermodynamic processes, then we will switch to laws of mechanics. We are still in review mode. Okay. First 3 classes are devoted to review of what you should know by the time you enter gas dynamics course. Okay. See you guys next time.